To start this problem, begin by factoring the polynomial in the numerator into x plus 5 times x plus 1. Since the factor x plus 1 appears in both the numerator and the denominator, they both cancel out, leaving us with x plus 5. Now set the expression equal to 0, and your final answer is negative 5. When dividing a fraction by a fraction, you flip the numerator and the denominator and change the division sign to multiplication. Factor a negative 3 out of the numerator and cross out the negative x plus 6 from both top and bottom, and then multiply straight across.
Exponential equations are solved using two methods. In method 1, each side of the equation can be expressed as a power of the same base. In order for 8 to have the same base as 2, you have to find the number that you raise 2 to in order to get 8. 2 raised to the third power equals 8. Write the left side of the equation as 2 to the 7x power times 2 raised to the third power. On the right side of the equation, it can be concluded that 2 raised to the 8th power equals 256. Write 2 to the 8th power with parentheses and distribute the 8 to the x. Because all the numbers have a common base, solve for the exponents. 7x and 3 are exponents that are being multiplied with the same base, allowing them to be added. Combine 8x and 7x by subtracting 7x from both sides of the equation to solve for x. X equals 3 is the final solution. In method 2, natural logarithms can be used to solve exponential equations with numbers that cannot share a common base. Add ln to both sides of the equation. Use the power rule to bring the 5x exponent down in front of the ln. On the left side of the equation, the ln and e cancel, leaving that equation. Divide by 5 for both sides of the equation. ln divided by 5 is the exact answer. By plugging the equation into a calculator, you can find the approximate value, which is 0.680 rounded to 3 decimal places. Solve the exponential equation as if it were a trinomial. You can use the guess and check method or the Xbox method to factor the trinomial. This is what the equation looks like in factored form. When the exponential functions are converted into the logarithmic form, e to the x power equals 5 is written as ln 5, and e to the x power equals negative 3 is written as ln negative 3. The only answer is ln 5 because logarithms cannot have negative answers. Logarithmic equations can have a log or ln on one side of the equation or on both sides of the equation. The log base 2 on the left side of the equation combines. The two logs are being added together, so they're being multiplied. The log 2 is being raised to the second power. FOIL the x plus 2 and x minus 1 to create a trinomial and solve using guess and check or the Xbox method. The factored trinomial equals this. X equals 2 and negative 3. 2 is the final solution because a log cannot have a solution that is a negative number.
Exponential equations are used to represent growth or decay model graphs and to model interest rates. More specifically, exponential equations can calculate the size of a population, represent interest compounded over a specific amount of time, or interest compounded continuously. Logarithms can calculate earthquake intensity measured on the Richter scale and was used on slide rulers to make multiplication and division easier. The base 10 in logarithms is used by chemists to measure pH and the acidity of liquids. Additionally, the base 2 in logarithms is used in information theory and computer programming.
Rational functions and graphs. A function is a set of points that do not share a domain. To determine whether or not a set of points is a function, you must find the domain and the range of the function. The domain in this situation is the x value, which is 4, 6, and 9. The range would be 3, 6, and 9, which are the y values. Since each of the domain values are unique, this is a function. Using this graph of a function, we can find the domain, the range, and the sum of f of -5 and f of 1. The domain is the x value. In this situation, it would be -5, -1, 0, 1, and 5. There is only one y value of this function, and it is 1. F of -5 is equal to y when x equals -5, and f of 1 equals y when x equals 1. Mathematical induction. Mathematical induction is used to prove statements about sets of numbers. There are 3 parts to mathematical induction. The first part is to prove that the statement is true for n equals 1. The second step is to prove that the statement is true for n equals k. The third step is to prove that the statement is true for n equals k plus 1. We will use mathematical induction to prove that this statement is true for every positive integer n. The first step is to show that S1 is true, so we set n to equal 1. Now we simplify. Since 1 equals 1, S1 is true. Now we plug in k for n. Now we will plug in k plus 1 for n. We must show that if sk is true, then sk plus 1 is true in order to prove that the statement is true for every positive integer n. Now we will use sk to prove that sk plus 1 is true. We will add the next term after 3 to the k minus 1 to both sides. This term is 3 to the k. Now, on the right side, we will put 3 to the k over a common denominator of 2. We will combine like terms so that the entire right side is over 2. We will combine like terms in the numerator, and then we will simplify 3 times 3 to the k. This equals 3 to the k plus 1 minus 1 over 2, which is equal to s to the k plus 1 from earlier. This proves that the statement is true for every positive integer n.
So in this problem, there are 1,000 juniors, which I'll shorten to J, 800 seniors, which I'll shorten to S, and 60 sibling pairs with 1 junior and 1 senior, which I'll shorten to P. Those 60 pairs, which I shorten to P, are divided by the total amount of juniors, which is 1,000, times the total amount of seniors, which is 800. When simplified, this is equal to 3 out of 40,000. In this problem, the sum of the total amount of balls is 21. Now take the number of blue balls, since the problem asks for the probability of the balls that aren't red or green, which is 7, and put it over the total number of balls, which is 21. When simplified, this is equal to 7 over 21, or 1 over 3. This problem asks us to use a license plate number that consists of 3 letters followed by 3 numbers. Since there are 26 letters in the alphabet and 10 digits to choose from for each space in the license number, cube 26 and multiply that by the cube of 10, since there are 3 spots individually for 26 letters each time and 3 spots for 10 digits each time. The final answer should round to about 18 million combinations.